Yeah, I flew in from Stockholm earlier today to come to this meetup and talking about AI and AI adoptions and listening to the other talks later. And first thing that struck me was on the airport that you have some technology and some AI adoption that we don't have back in Stockholm, Sweden, and that's the e-gate. You've all seen it at Heathrow, right? You go there with your passport, you just put in your hand, press down the passport, and you look into the camera and the gate opens. That's a really, really cool adoption, especially in theory, since when I tried it, it didn't open. And I had to go to this line for manual inspection anyway and stand there for 40 minutes roughly. But that's just that's a side note. I'm Andreas, and I'm from I work with a team and a company called Peltarion, where we develop something that we call operational AI platform, which is, I think it sounds cool, but it doesn't say too much. But in essence, it's a platform for you to rapidly develop deep learning solutions, even if you don't have the interest in coding everything from scratch yourself. And I want to talk more about that in details. But also, before that, I will talk a little bit about AI adoption that we have today in companies, and because we want to make that more rapid and improve the rate of adoption. And then I will end with running a case on screen, a real case. And I don't want to spoil it now too much, but it's about music, and it's going to be an interactive one where all of you can use your phone for some voting, which everyone likes voting, right? So we're going to do that. So let's see. I also have a habit of explaining the agenda before I show the slides, so I think we can just skip this one now. So so deep learning, there's really a revolution going on there now with all these adoptions. Say, for instance, the e-gate thing, where it films your face, and after a few seconds, it can identify you, match it with what you have in your passport, and opens the gate, right? And that's really, really cool. And it probably does it with a really high confidence level, since I didn't get in. I think it's because I took my passport photo without glasses on, and I had my glasses in the gate, so it didn't work. But I want to have a certain confidence level, of course, to do that. And this is really cool technology doing this. I mean, it was, go back 10 years and you didn't have it. It was really difficult to do it, maybe even impossible to do it. But now we can do it. And why do we have a lot of deep learning applications today? So one reason on foundation, as many as you know, is that you need to have a lot of data, lots of data. And a very good way to find that is the internet, obviously, and generates so much data. And I read somewhere that a double amount of data on the internet every 2 years. And also, for instance, just YouTube alone, every minute, there is roughly 300 hours of video uploaded on YouTube. And about 10,000 tweets are written. I read this on the internet, by the way, so it must be true. But I'm not certain about this, but probably in the ballpark. And even if I'm a frequent user of both these platforms, so probably you could just delete 99.999% and still be happy. But anyway, it's a lot of data out there, right? And as a developer, you have more data. You also increased all the power in the infrastructure, a lot of development going on with new GPUs and hardware to calculate all this. And of course, a lot of algorithms and tooling to be able to actually do something out of all this data that we have. And so obviously, if we can use these technologies right that we have today, we can all benefit a lot from it. And we know about a lot of cool applications today, cool and useful, by the way, within healthcare, for instance, where you can get help predicting cancer at a very early stage, which is awesome, of course. And you can help translating documents and things you write very quickly, so you can have a easy time communicating with people all around the world, and in that way make a more open world where everyone is included. So it's cool, and yeah, you can do this to fight climate change, of course, and reach other of United Nations sustainability goals, and you can also maybe use it to find a cure to the coronavirus, so Peter doesn't need to be scared about that anymore, which would be great. All right, and some big companies are really fully committed to doing this, right? It was a few years ago now, or a number of years ago now, that Google said that, okay, we've been mobile first. Everyone is using mobiles today, and it's, yeah, you have it on your phone. But now we're going to be AI first. And that's what we're going to do. Build a lot of applications on this technology. We're going to go heavy on research, and that's what they've been doing now for a long time. And there are other companies doing the same. So you have a Netflix, for instance, creating great algorithms to help you with help you say what you can binge watch next, or you have speech recognition and so many different applications. And one of the reasons they are successful, so I feel a bit dry in my mouth. I have some water. One reason they're very successful is that they have a lot of money, obviously, and can put into research, and they also have they can also afford trying out something for a while, see if it works, and just drop it if it doesn't. And so many cool things comes out of this. Of course, you have Siri, you can talk to Alexa, and you have just so many things that you use in your daily life. But it can be really expensive, and we have Deepmind, for instance, doing so very many cool things that we can do. We have AlphaFold, for instance, that I read up on a while ago, which help you predict the 3D structures of protein just based on the gene sequence. Very difficult problem, and very, very cool. And also they've made, you know all of this probably, but I'm saying it anyway because I think it's fun and cool. And you know, AlphaStar playing StarCraft. Are you up to date with what's going on there? Yeah? Some of you are nodding, so. But anyway, I played the game StarCraft back in the days, and I think it's really cool now to see how the algorithms are developed so you can actually beat grandmasters in this game. But it costs a lot of money, and you need to try out things, and not everyone can afford that. So how can we help adoption and the adoption rate of these technologies? So of course, if you are a startup, you have a lot of good ideas on how to improve technology for humans and come up with good things. Or if you're a business that want to make more money, coming out with new products and whatever, there's a high chance that you can profit a lot from using these new and latest technologies. And let's see. So one obstacle for many companies are the technologies that they need to learn. So you have an infrastructure and you have processes for developing IT projects. You've done that for a long, long time. But now you need to develop AI projects instead, which is very different in many ways. And here on the screen is just a number of different technologies. Of course, they're not all mandatory to build a new project, but this is a picture of the landscape that you have to deal with. You at least need to know some of the technologies in every step here for a successful AI project. So let's see. So I'm building an AI proof of concept. You can do that depending on what you're doing, but you can do it usually with a quite small team. Maybe it's you and two more people, or maybe even just you if it's small enough and you're skilled enough, then you can do it by yourself. And you sit there, you work with PyTorch, TensorFlow, build something, and but then when you want to put it into production, there's a lot more to it as well. So you need more other skills. You need to cooperate with different people within the company to make this happen and to have a real application where you really leverage on this and take and build the cool application at the end. I realize now, watching on the slide, that model seems to be a very, very small part of the AI project, which is obviously not the case, but it just shows that there's many other things that you need to think of as well to make it all happen. And then in a typical company where you have the data science department up and running already, it can look something like this, that you have isolated business areas and isolated data science department, that you have something you want to, let's say, work on one department. You're not a data scientist in this case. And you have an idea what you want to try out. You want to build a project. So what you do then, you call your data science department, and you set up a project and run everything from scratch. And the data science department might feel that sometimes, of course, it's a cool project coming up. This is going to be fun. But also sometimes it's like really minor things that are maybe too simple, or like routine work as well, that you think like, do I need to do this? And so an idea to get this, to increase the rate of adoption of AI is to change that a little bit. So every department itself, it can work. It has some AI skills or tools to work with that, to build simple projects themselves, to try out things and see how that goes, and integrate it. So of course I can't do everything, and a data science team is still very much important here, helping the departments with the data science still, so it runs smooth, but also hopefully having more time on focusing on more challenging things. So we really need to know the tech behind and knowing the algorithms to make it work. I see here as well that the data science department, it feels like everyone is fired and it's on its way out. That's absolutely not the case. It's more on the side and can run its own projects as well. So what do we do then as a company? So we are building a platform that we call operational AI. And it's basically a platform where you can, using a graphical user interface, you can have a look at your data and you can build your models. You can have a wizard to do that, selecting the right model for you. Where you also can do your training, you can evaluate it, and in the end you can also deploy your model. So the idea is that you come up with an idea, you don't have all the skills, you're not a data scientist yourself, then you can do this to build something, and build proof of concepts, and finding a use for it in your business in that way. So with that said, I wanted to go through an example of something we built on the platform and have a look at that. And it's 2 steps. First, I want to go through a little bit of theory, since we're going to work with music now. So I just want to walk through how that works on a quite high level still. So, and then we're going to have a look at the case as well, how it's built on the platform, and also try it out live. So let's do this. So working with audio, one way to do that is, since there's been a lot of focus on developing algorithms for image analysis for a long time now. It's been a really cool area with a lot of research, and this shows a little bit of the progress that's been going on for the last 10 years soon, and how good the algorithms are at some image classification tasks. And one idea here, and one way to approach music is to use the same algorithms for that as well. There are many ways to do it, but one is to use image classification algorithms as well. But then to do that, since audio isn't images itself, or we don't think of it as images, so we need to find a way to actually turn music into images. And we're going to do that using something called spectrograms, which I know some of you know of, but not all of you, so I'm going to talk about how we build that from audio. So how many of you play an instrument? All right, quite many, half roughly. Yeah, good. So you may have seen notes like this before. I don't know exactly what song that is, but trying to sing it in my head now, but I don't reckon it. But anyways, from this representation, this is one way to represent music, right? You can just read out that you start on a high note here, you go down for a while, and then you go up again. And you can read that, so you can actually maybe sing it in your head if you're a good singer. I don't read notes myself. I play music though, but you could do that. And the next one, it's a waveform representation of music. So that's what happens now when I speak into this microphone. The microphone picks up the changes in pressure in the air, and it samples it. So one sample for every time frame, kind of. So depending on what you have a sample rate, maybe you have 44K samples per second. So that means 44,000 lines every second. So that's a way to do that as well. So what you can see here is this is time axis, and here you have pressure, basically. So this new form that I want to introduce for those of you that haven't seen it before, is the spectrogram, which is, we zoom in on that one here now. So you still have the time axis here, going there, and here we have frequency instead. So for every time step, you can see what frequencies are involved. And you can also see the intensities of each frequency. So that would be down here, you have the bass notes, like doom, doom, and up here you have the high pitch. And so to solve this problem now, if we find a way to make sound into spectrograms, then we can use these pictures, that is the outcome of that, into our algorithms and use the same technology for finding patterns in music. And which, by the way, is very cool that you can use the same technology for different problems. And it's not just music or audio, you can also use it for radio signals or what you want. So this is just to give an intuition of spectrograms. So I have 3 spectrograms and 3 different audio samples here now. So the idea here is that we as humans as well, we can kind of see the sound playing. So let's try the first one and we can see it. Listen to it and then let's see. So we hear the beat here, it's like a bass drum, like doom, 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 and a snare. So it's hard to see just first time you see this one. Okay, this is a bass drum and a snare, it's quite difficult. But if you've seen this a few times, then you can definitely recognize it and come back to it and see that, okay, that must be a bass drum. Okay, try the next one. Can you see that as well, how it works? So, do, 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 do. As it goes, so time here and frequency there. Same thing here, if you see that a lot of times, then you can probably recognize this sound, just looking at this picture. Okay, so any guesses on the last one? What is it? It's a yeah, that's a difficult one. So that's a bus, and you can hear it's like all over the spectrum, right? It's the bass voices, and you have some sound from the brakes and people shattering, and yeah, just all over the place. But anyway, these are, when you listen to them, they're very, very different from each other. And you can also see that the spectrograms are very different. Oh. All right. Let's see, didn't mean to do that. So let's have a look at how we can go from audio or this waveform representation, because this one is really easy to get. It's just recording what I'm saying here. So let's have a look at how we can turn this into a spectrogram, because that's what we want to put into the algorithms, remember? So thing is, it turns out it's quite easy to do it. There was a guy in the, what was it, early 19th century, I think, called Joseph Fourier, that came up with a way how to do that, going from this waveform to and find out the frequencies in it. Yeah. If you want to take a picture, I can take a break here. Yeah, I'll send out the presentations as well later so you can have a look. So, yeah, and I'm gonna, yeah, you don't need to remember this formula. So, and what you do, when you apply it, you can apply this formula once for the whole signal. What we will get that is just a one-dimensional array. So you will get all the frequencies, but like all the frequencies that define in the whole signal at once. So if you have a long signal, that doesn't make too much sense for this kind of application. So what you want to do is you chop the signal into many small pieces, usually somewhere around maybe 100 milliseconds, something like that, depending on your application, of course. But in this case, we did roughly 100 milliseconds. So you take this little piece here. So, and then now we just zoom in on that. So we go from here, we zoom in, we get this one, right? And for this small piece, then we apply the algorithm that all of you probably remember, no? And then you get the first slice of the spectrogram as well. So 100 milliseconds from an original signal would be 100 milliseconds of the spectrogram, right? And then you just do this for the whole signal, one slice at a time, and then you have your spectrogram. And if you are a coder, all you need to do is one line of code, basically, to do this. So it's quite cool. And it can do that for you. It's amazing how these libraries work. So like, you just want to create this, you know about the spectrogram, and then just Google like how to make spectrogram Python, and then you get this. It's cool. All right, and then we put this through a convolutional neural network, which will give us some probability of different classes. And I see now that I didn't present the case, so it doesn't make too much sense now. But let's do that instead. So what I will do now is now we went through the theory, right? So now I'm just going to show how we apply this for a customer and then we will also listen to it and see how it works. So we did that for a company also in Stockholm, Sweden, called Epidemic Sound. So have anyone heard of them? Yeah, cameraman, heard of it? Yeah. And so basically what we work with is music licensing. So say you sit with your vlog, you want to put it up on YouTube, but you want to have some cool background music when you do whatever you do on your vlog. And but then it can be really difficult to get license for this music. So maybe you go into Spotify and listen to a song, and then you call up Justin Bieber and ask if you can play it in your vlog. Maybe it works, but I don't think so. But these people they have a huge library of music, tens of thousands of songs, and they label each song with categories they came up with, such as like dreamy, ambient, angry, a number of categories, labels, right? So you as a user, what do? You pay a subscription to these people, of course, and then you go in, just browse the categories, and you find a song, and then you're free to use it on your videos. So it's a good service if you work with. How many vloggers do we have in here? Anyone putting into any content onto YouTube frequently? No? Do you put content on YouTube? Okay. No. So that's what you do. It's quite simple. So, and the application that we want to have is they want you to go into or what they want to do, the problem or the issue that we're working on. Let's go back to this one. I was a bit quick now. So what I want to solve is today they buy in songs from a number of artists, and then they have on their and then Epidemic Sound, they have people sitting down and manually tagging the songs. They'll listen to it and put tags on it. So there are two problems with this. One is it's very time consuming and not always very fun for everyone involved. And also you will have a lot of inconsistency in your database, right? So if you listen to a song and I listen to the same song, it's quite likely that we will, it will enable different emotions in us. Maybe depending on the mood today, or just that we have different taste in music or whatever. So that's what we want to solve, and that's why I want an AI to do this instead, because it will be much more consistent doing it. Maybe wrong in some subjective sense, but still consistent, right? So then we build they build actually the front end for this, and they send. So what they do is the input is a new song, right? They get a new song from a new artist. They send that into our backend that will put labels on it, a number of labels. I think it's up to 5 labels or so. And then they just take that and store it in a database. So something like this. They have 3 songs, and they generate the spectrograms from these, send into the model that we trained, and back goes the labels like peaceful, ambient, dreamy, smooth, dark, happy, dreamy, and all these. So they save a lot of time, and it will be more consistent. And now I have some screenshots of the user interface. We can have a look at that later if you have some more time. But just let's have a look at how we do that on the platform in our tool. So here we have uploaded the spectrograms from the songs, and that's very easy to generate, right? You had a look at that one-line code earlier, and then you just zip that together to a file and upload it to our platform. And what happens here is that, and this is for the training data, right? So they are labeled already. So you can see that you upload spectrograms. This is inspecting what we just uploaded. You can see the spectrograms, and then you see all of the, whatever it is, like 30 or 40 labels, one hot encoded. So, which means it's a 0 if it's not angry, and it's a 1 if it is angry in the first column here. So that's an inspection, and then you select here on your left side to keep some of it for training and some of it for validation, right? And then you go through, in the system, we don't see it on the screenshot, but then you just press a button up here called Wizard, which recommends your model for this kind of data. And then it puts that on the canvas where you can sit and build your own models if you have an idea of what you want to do. Otherwise, just using the ones that we have in the system. And it's a lot of pre-trained models as well for ResNet and whatever you want. It's quite a lot of models in there. And here from this page as well, you can select the epochs and learning rate, or you can just stick with the defaults. And then we press train, and then it starts training, right? And as you know, probably it can take, sometimes it's really quick, and sometimes it takes days and hours. And this will run now on the servers with the GPUs. It's quite quick to do that. And while it trains, you will see the progress. You can get a lot of different data here to inspect the progress as you go. And then when you're done with the training, if you're happy with the results, then you can press a button to deploy it. And when you press that button, it's just one button, one click, then this model will be available using a REST API. So then just send in your next song as a spectrogram and you will get back the results. All right, hope it makes sense. So now we come into the interactive moment. So please put up your phones or computers. And what I will do now is I will play 2 songs, and for each of them, you will be able to you can go into this URL. Hopefully it works. And hopefully that code is activated as well. So you won't see anything on this page yet. It will just be blank. But what we will do, I will start playing a song, and then it should probably pop up a lot of options on it. Categories like angry, dreamy, happy, whatever. And then you're allowed to select up to 3 of these and then submit it. Okay, great. So now I'll play the song, and then you have up to 3 choices, 1, 2, or 3. And then you press submit, okay?
Five to 10 minutes.
5 minutes.
5 to 10, yeah. But this is cool.
That's good. Yeah. I'll skip the yeah.
How do you process the lyrics? What about the lyrics?
So we don't explicitly handle the lyrics.
So it doesn't have any effect?
No. Or, I mean, it has indirectly, because the lyrics, it will affect the spectrogram, right?
It's just the sound of the lyrics.
It's just the sound of it, exactly. But you don't know exactly what the network learns. It might learn the lyrics, right? But you don't know that.
Yeah, some songs, the whole tempo and everything will sound upbeat, but the actual meaning of the lyrics is very dark.
Exactly.
But yours won't.
It would be cool to try with a song like that, where the lyrics like contradicts the feeling of the song. Yeah. But no explicit training on the lyrics. Yeah. Just the spectrograms. All right. I really like that song, by the way. It's nice.
It's quite slow, very nice, it's a romantic movie, basically.
Romantic movie.
Yeah. It's a very romantic background.
Yeah, I agree. It's really, really nice. Okay. All right. So let's see. And this is what you can see here is what I want to show as well, because now we are, let's say, how many are we? 64 participants in this, and let's say they have 64 people at this company as well labeling the songs. It might look, or probably would look exactly like this. So I mean, we touched so many categories, but it's a maximum of 3 or maybe 5 categories. I don't remember, but anyway, they have like a maximum number of categories, right? And this means that we don't really agree with it, like 100% on what labels it is. So we can see that most of us think it's dreamy, sentimental, also relaxing and hopeful, those kind of feelings. But someone think it's angry, and someone think it's yeah. I mean, maybe someone just don't like guitars, right? Makes you angry. So you don't know. And the same 2 people think it's dark, and it's still yeah. So, but let's see what the computer says. I have named the button show correct answer, which might be not right, but let's see what happens. Okay, you can see that's so the computer selects peaceful and sentimental. That's the 2 categories.
Not dreamy.
No, it didn't pick dreamy. I agree. I would probably pick dreamy as well. But what we could do is go through the catalog and listen to other dreamy songs, because it might be the neural network might have a different definition of dreamy in some sense. Yeah. But anyway, sentimental and peaceful, which is something most of us think.
Your network, is it trained with the same amount of data? So enough samples for all type of the...
No, it's the same amount of samples for it. Yeah, yeah. All right, we have time to try one more. So, all right, are you ready for next one? Yeah. All right, so what have we got here? Angry, 18 people. Yeah. Busy, frantic, chasing, restless, running, suspense, epic. Yeah?
It's more like the sort of beginnings of rock bands in 1980s, early 80s, 70s.
Yeah,
That
yeah.
sort of background, actually.
Yeah. It's not a romantic song anymore now, right? So, but we have one person saying dreamy still. So, all right. So let's have a look at what the computer says here. So the computer says chasing and angry, and feels like most of us kind of agree with that as well, even if it didn't catch all the labels that we think. Pardon?
Is the algorithm only choosing 2 categories rather than...
I think it was limited to 3 or 5 even, but it's only picking 2 now. Yeah, probably because of the, it needs to reach a certain level to decide on it. So like maybe the threshold is 80% certain or something like that. All right, but yeah.
So in your user face, it looked like you only sampled 30 seconds of the song.
Yeah.
There were 2 columns there. And I think this
Correct.
song is a good example where the beginning, because I saw people tagging in the first few seconds,
Yeah.
and then once the drums are so set in, then the answers changed quite significantly. So how do you make sure that whichever part of the song you sample is actually representative of the...
That's the thing they're actually working on today. So it's a really good question, trying to find out like what's the best representative, what part of the song is most representative.
And did they put this in manual? So there was a person who said, this is the 30 seconds we want to sample, or did you have an algorithm to determine that?
Here we just picked a part of it, kind of random, from the songs.
Random.
Of part of the song, yeah. Which of course, just as you say, won't give you the best results all the time. I mean, this song is one sample, and also Bohemian Rhapsody is really difficult to, but that's also hard to put a label on it, right?
And is it because of computational resources? I mean, obviously, if you sample the whole song, you have to deal with more data. So why is it only 30 seconds?
Yeah, it's basically for computational reasons. Yeah.
Thanks.
Good,
Is it
thanks.
because your network needs to take in 30 seconds worth of data and you can't handle different sizes?
Pardon?
Is it because your neural network can only take 30 seconds of data and not deal with different...
Yeah, we designed it to just be able to take 30 seconds and only work with 30 seconds for computational reasons, I feel. 1 minute? Yeah. A last question? Yeah?
Is your platform like aware that it's being fed a spectrogram and adjusts the architecture to that fact, or is it using the same ResNet that it would use for a picture? Because, well, spectrogram is like structured, right? The dimensions mean different things.
Yeah, it does. So that's a part we are going to add to the wizard as well, so you can actually have like a look at the images and see what it finds. But right now it will just give you a vanilla CNN to run it. Yeah, but that's it's in the pipeline. With.